Good morning, people. Boy, got a full house today, finally. And I've got color in my face. Hello, James Ferracci. Good to see you. What class do you usually have at this time?
Biochem.
Biochem. Okay. Is that Dr. Kless?
Mm-hmm.
Is she the only one who teaches biochem now?
No, Dr. Thyssen teaches it as well.
Thyssen. Okay. 1, 2, 3, 4, 5, 6. I guess I should do this. I count 11, so I got 10 people here. How many people are in this class? I keep asking that question. I guess I should know, being the teacher. Okay. All right, let's bring all your faces up so I can yell at you. It's hard to yell at names. Oh, I love your background, Dante.
Thank
Matt Bernhardt, getting ready for his post-graduation job as a lumberjack. Matt Camellan just rolled out of bed. God love you. God love you. And he's got James Ferracci's shirt on. Show your shirt, Matt. And Tyler doesn't have a camera, so that's fine. All right. I guess this is the biggest class we've had in a while. Let's just go ahead and get started. So first thing I want to do is talk about the quiz, the review and the quiz I sent over this weekend. Okay, did you guys all read this over? Everyone just say yes. Yes, we read it, Dr. Schlichter. We studied it. Yes, yes, it's very good, very useful. Okay, so this first part is kind of the way I see all of biology, not just as individual events, but as everything tied in together. So we've gone over a whole lot of stuff in this class so far, everything from receptors activating or drugs activating receptors to second messengers to the physiology change in the cell. And now we're stepping back and looking at the overall physiology and why these things are going on. In the next section of notes that will start next week, we're going to start talking about blood pressure and how the heart and everything works together to do that. And then we'll get into disease processes, what happens when it goes wrong. But I want you to start thinking like this. When blood pressure drops, a baroreceptor on the aortic arch is activated and sends information through the afferent neurons to the dorsal root of the spine up to the medulla oblongata. This sends info down to the sympathetic efferents, which come out the ventral root of the spine. And those presynaptic sympathetic neurons are short. So shortly after the nerve comes out of the spine, there's a ganglion, which has a nicotinic synapse, which are nicotinic acetylcholine receptors, which are sodium channels. So they cause stimulation of the postganglionic neuron. This goes over to the SA node, or one of them does anyway, over to the SA node, releases norepinephrine. Norepinephrine activates beta-1 receptors on the heart, right? Beta-2 is the lungs, bronchi, which increases cyclic AMP to GS. And in the heart, that SA node, you've got your funny current, and the funny current is cyclic nucleotide controlled, so cyclic AMP directly opens these HCN channels, and that increases the slope of spontaneous depolarization of the SA node and increases heart rate. Heart rate goes up, blood pressure goes back up. Okay, so that's your reflex loop. And you should know all the nodes along that and what second messengers are involved and everything. So, based on the description above, can you do the same thing for negative chronotropy? I want to hear James Ferracci do this one because you're the first name up on my list here. Everyone's going to get picked on. Don't take it personally. You can just look at that paragraph and just change some words here and there and you get a similar response. You're muted. James? Oh, you did that on purpose. Oh, okay. Who just came? Kaylee Quackenbush is here. Yay, Kaylee.
Sorry, I actually didn't get the quiz. I didn't see it until.
Oh, Jesus.
Okay.
I'm sorry.
But I'll try. Wait.
I always send it out. I think I sent it out by email, and I always forget to append you to that because you're technically independent study. Okay, you're off the hook. But
Thanks.
What's that?
I didn't see that quiz either, though.
No?
No.
Okay, well, let's just talk about it then. This was, I think I put it up in, I'm sure I put it up in Moodle. I think I put it up in Moodle. I thought I emailed it to you as well. Maybe not.
C is the norepinephrine, epinephrine, and iso.
Right, we went over that one last Thursday, I think. Yeah. So this is one I put together this weekend because Thursday I said I'd give you another quiz, and I didn't get it up till probably at least Saturday. I think it was Saturday I got it up. Well, anyway, let's just do this. Okay, can anyone, and I'm looking at someone to pick on, Matt Bernhardt, you think you're smart. Let's have you answer this. So basically just go back to this paragraph and follow the same pathway, but the difference is blood pressure increases and the baroreceptor responds. What happens here? You're muted, Matt.
Yeah, no, there was a reason for that.
All right, well, let's just do this together since, and when I say let's do this together, it basically means let me do it, you people. Okay, so let's just go through this. For example, well, let's go through and I'll ask people questions as we go. So, all right, blood pressure increases. Baroreceptor arch is activated, sends info through the afferent neurons to the dorsal root of the spine. This is all the same, okay? This sends info down the what? What are we going to change here, Dr. Ramos?
Parasympathetic?
Parasympathetic. And what's the name of that, the parasympathetic efferent? The main one that comes from the 10th cranial nerve. I lost Ramos.
Yeah, you did.
There you are.
I don't know.
Ooh, Farachi's got to know this one. What's the 10th cranial nerve? Your main parasympathetic nerve?
Vagus.
The vagus. Okay. Vagus nerve. Well done. Noemi got that one too. Well done. Okay. So the vagus nerve, which come out the ventral root of the spine. Now, how about this? How are we going to change this for the parasympathetic nerve? Oops.
Isn't there like a longer distance between like the next ganglion?
Correct. So with the vagal nerve, with the parasympathetic neurons, you've got a long preganglionic thing. So instead of shortly after the nerve comes out of the spine, you would say shortly before the effector organ, right? So the ganglion is close to the effector organ, which is what kind of synapse is that in the parasympathetic side? The ganglionic synapse is what kind of, Ariana Sotar? So I'll show you, we're right here now. Are we gonna change this?
Would it be muscarinic?
Nope. We're talking about the ganglion.
Is it norepinephrine?
Nope. Parasympathetic ganglion. Oh, you guys are not ready for this test. You guys are not ready. I'm so glad I didn't do a test today. You guys would be totally screwed. This is exactly the same, okay? So at the ganglion, it's the same for sympathetic and parasympathetic. And that's important because we'll have a drug that we'll talk about today that's going to block that ganglion. So you lose both halves of the autonomic nervous system. Okay. Très disappointed. The postganglionic neuron goes to the SA node and releases what? Parasympathetic neuron is going to release what? Ariana, go ahead. Say it again. What?
Epinephrine?
Back up to your last answer.
Muscarinic receptors.
Okay, so this is, this is parasympathetic, so this is acetylcholine activating muscarinic receptors, and what are they going to do? Let's say
Decrease cyclic AMP.
decrease cyclic AMP through which G protein?
GI.
Okay, and because you've got a decrease in cyclic AMP, that's going to decrease the amount of funny current. And what's that going to do to the slope? Increase or decrease? Okay, decrease. You guys, I swear to God, where you been? I guess you haven't been studying this shit. Okay. All right, so just to go through real quick. Blood pressure increases, the info goes back to the medulla oblongata. This sends info down the vagus, which comes out the ventral root, or it's your 10th cranial nerve. I guess that's a ventral root, I don't know. And goes all the way to the heart. Then you've got a ganglion. And at the ganglion, you've got a nicotinic synapse. The short postganglionic neuron then goes to the SA node, releases acetylcholine that activates a muscarinic receptor. I believe it's an M2. Yes, M2 or 4, which decreases cyclic AMP. And with less cyclic AMP, you get less funny current, and that's controlling the slope. So this decreases the slope, and you get increase in heart rate, or decrease in heart rate. Decreasing heart rate then will then bring your blood pressure down. Okay, let's go on and answer some more questions. Mike West has been sitting there like he knows what he's talking about. Let's see what Mike West is up to. Based on the mechanism, oh, everyone gets a chance at this one. How many people we have in the class today? 10? Perfect. Everyone's going to get picked on today because I hate you all equally. I don't want to be show favoritism here. Based on the mechanisms of smooth muscle and endothelial relaxation, list 10 possible mechanisms of action that could cause an artery to relax. Describe how this causes relaxation. Remember that a drug is a molecule that binds to a protein, either activate it or block it. So I love this question. I ask this question on every test in every class I give, because it's kind of like an open-minded, there's 100 answers to this, just give me 10 of them. Okay, so let's start with, I'm going to start on the bottom this time. James is on the top. I'm starting on the bottom. I know I said, Mike, I would give it to you, but Kaylee Quackenbush. Kaylee, can you bring your face up here? Okay, so we've got smooth muscle contraction and smooth muscle and endothelial cells. So we talked about a lot of mechanisms that were involved in controlling contraction of the smooth muscle cell, which involved both inside the muscle cell itself and endothelial cells affecting the muscle cells. So what is a drug? What drug would you use to relax the smooth muscle? And remember, the drug can activate or inhibit any protein in either mechanism. So you've got both the easiest and the hardest job because there are so many possibilities now, but you don't know how to address the question yet.
I have no idea.
Okay. What causes contraction of the smooth muscle?
I don't know.
What receptors did we say were important for contraction from the sympathetic nervous system?
I don't know.
I've lost her. I think she's mad.
I'm not mad.
Okay.
Sorry, I'm trying to look at the notes. I have no clue.
Okay. All right. Well, let's move on to the next person to bother. Noe. No. Last person is Tyler Montano. Either answer the question I just gave or just give me a drug here. So, how are we going to relax smooth muscle?
Calcium channel blockers.
Calcium channel
Those are-
blockers. Okay. How does that work? What were they important for?
They lower blood pressure by preventing calcium from entering the cells of your heart and arteries.
Okay, right, right. So those Voltschmidt calcium channels on the cell surface, when the cell depolarizes a little bit, they open, they let calcium in, and that causes contraction. Another reason why they're really important is because when I was in grad school, my advisor had the slush fund from some drug company because he did a lot of work on calcium channel blockers. And he'd take us out to really great dinners because it wasn't like an NIH grant where everybody wants to know where the money's coming from. He'd take us to these really fancy dinners. That's another important thing about calcium channel blockers. Okay. Noemi Alonso. Noemi Alonso. Give me another mechanism. So he's going to block calcium channels. What are you going to do? What you going to do?
The beta 1 adrenergic receptors increase cyclic AMP.
What are you going to do? Activate or block?
Activate.
Correct. Good. You could give a beta agonist, and that would cause the artery to relax by activating beta receptors, increase in cyclic AMP, and then you've got all those other targets in there. Okay. Nicole Lamberton.
I just got back inside from bringing my dog out. I'm kind of lost right now.
Okay.
So
What's your dog's name?
Atlas.
Atlas. Okay. Come on, Atlas. Well, we can move on. You hang out for a bit. I'll ask you again.
Which
Oh,
one are we
Pheasant.
on? 2?
What's it?
Are we on number 2?
We're on number 2. So think of a drug that could relax smooth muscle. So basically, you're thinking about the mechanisms of contraction and relaxation of the smooth muscle. Find a drug that would cause relaxation.
So the drug or the mechanism?
The drug, and what mechanism does the drug use?
Okay.
Basically, the drug's going to bind to some protein, either activate it or block it, and cause relaxation. You guys are so screwed Thursday. Oh, I'm not taking my foot off the gas either. Thursday is going to be a tough one. Okay, so let's back up to what Noemi said. She said she's going to have a drug that will activate a beta receptor, and that'll produce relaxation through the cyclic AMP mechanism. What else could you do to increase cyclic AMP? Basically, any protein in the path between the receptor and the response could have a drug that would activate it. How about, what does the receptor do? Once you get an active receptor, what's the next step? I'll give you a hint. It's a G protein coupled receptor. Nicole, are you answering or are you unsure? Because you're muted. You're muted, and I'm like, does she know I'm still
right now.
talking? Do you know I'm still talking to you? Okay, let's move on then.
I wasn't sure if you were still talking to me. You said you were going to move on, but then I wasn't sure if you were just talking to the class. Sorry.
I love Zoom. It's so confusing. I'm
trying to figure it out. I don't really
move
know.
on? Should we move on to
Yeah, I
someone
didn't
else?
think you were talking to me.
Okay, because Celine's on the edge of her seat there. She wants to answer this.
Well, I think of something different. So like, if you like activated myosin light chain phosphatase, wouldn't that keep like relaxation occurring?
Yep, that's a good answer. There are no drugs that do that, but that would be a great target because you activate that phosphatase, you're gonna dephosphorylate the myosin light chains faster. Good answer. All right. See, I wouldn't have thought of that, but that's a good one. James Faraci, how about you?
I'm not sure if this counts because it has to do with the calcium, but
Okay.
you could do an alpha-1 antagonist.
Alpha-1 antagonist, good. Yeah, because the alphas are the ones that are contracting. If you block the alpha receptors, that'll cause relaxation. Excellent. Good answer. And there are a lot of drugs that do that. We talked about them in one of the lectures, and I'll expect you to know the names of drugs too. Okay, Matt Bernhardt, you're next on my list. How would you relax this smooth muscle?
Well, I'm looking at a slide that says that the contraction is based on the neurotransmitter norepinephrine. So you block that. That might be what James just said.
Well, that's what James just said, because he said block that alpha 1 receptor, and that's, yeah. So
that was my big firepower that I had.
Well, follow that path and go down and see what else is on that path that you could inhibit or activate. What does the receptor do?
Well, after that, it sends a little thing to PLC.
Okay.
So you can inhibit that.
Okay, what would that little thing be called? It's a G protein. It's called GQ. So you could directly inhibit that GQ, and then it couldn't couple to phospholipase C, and that would cause relaxation too. Okay, Mike. I should tell the people who's on deck because Mike seemed a little lost there.
No, I'm good. I lost my thought for a second.
Okay, so we just blocked the alpha receptor, then we blocked the G protein. What's our next step? What else could we block?
How about something that competes with the GCPR and knocks out Rho A?
Rho A. Oh, that's the other pathway, isn't it? Yeah, I forgot about that pathway. Yeah, so like a competitive inhibitor of the interaction between the alpha receptor and Rho A. So Rho A then activates the ROX, and that inhibits the myosin light chain phosphatase. Am I right about that? I just learned that this year, so I never heard of that pathway before. Good. Okay, Mike. You get a star. Dante Quinones.
I was gonna say myosin light chain kinase.
Myosin light chain kinase. What are you going to do? Activate it or block it?
I was gonna block it.
Good. Block myosin light chain kinase. You don't get phosphorylation, and you get relaxation. Okay, Bezowit. What do you think?
I'm not sure, but I think we can decrease the stimulation, which turns off the IP3 production.
Well, we kind of did that already by blocking, well, so far along that pathway you're talking about, we've blocked the receptor, we've blocked the G protein. So what else do you want to do in that pathway?
How about if we try NO to relax the arteries?
Ooh, there you go. So you can directly release NO inside the smooth muscle. And what's that going to do? What's the pathway there? What does nitric oxide activate?
I'm not sure about that. This is found in the endothelial cells. Is that GC?
GC, guanyl cyclase, correct. And then that produces guanyl cyclic GMP, and that causes relaxation. So that's our endothelial cell. Well, no, it's not. It's just NO directly in the cell. Okay, I think you've all been sufficiently chastised. Oh, no, you haven't. Ariana Totarum. See, she was going to be upset with me for not asking her, but I brought you up. Okay, go ahead.
Well, I was going to say nitric oxide as well, but can't you block your IP3 production, which will decrease calcium?
Okay, you could do that. You could block phospholipase C. Maybe a drug that blocks phospholipase C. That would work. Okay, well done. Well done, my friend. Oh, Matt Gamelin sitting there thinking I forgot who he was. What do you got?
Could you block the polymerization of actin to stop the cross-bridge cycling?
That would work. I think it's a bit drastic, though. That's a big step. It might have a lot of side effects for that, but that would work. Yeah, I don't know. Not the best answer.
All the best ones were taken.
What's that?
All the best ones were taken.
I still know a really good one no one else has gotten. Cyclic AMP causes relaxation. How can you increase cyclic AMP besides to the receptor and the G protein and all of that? You could directly activate adenyl cyclase. There's a drug that does that. You could block the phosphodiesterase. Okay, so then that would cause an increase in cyclic AMP. There's also a phosphodiesterase that breaks down cyclic GMP, which you can block. That's what Viagra does. What else? We didn't really touch on the endothelial cell at all. You could have an agonist that activates IP3 production in the endothelial cell. That would cause activation of nitric oxide synthase, which would produce nitric oxide and cause relaxation. You could directly activate nitric oxide synthase and make NO. You could activate the G protein in the endothelial cell to activate that whole pathway. So kind of what I'm getting at is you got to know all these pathways, and like any activation or inhibition in this pathway is going to affect it. So how does it contract? Receptor activates G protein. So you could block the hormone from binding to the receptor. You could activate the G protein directly or inhibit the G protein directly, inhibit phospholipase C. You could inhibit protein kinase C, which is activated by diacylglycerol. You could inhibit the calcium channels, which Tyler Montano did. You could block the IP3 receptor on the SR. You could activate the myosin light chain phosphatase, which someone said. You could inhibit the myosin light chain kinase. Basically everything on that pathway. What else? Caldesmin. Maybe you could block calmodulin's ability to bind to caldesmin by putting a drug on caldesmin. What else? The endothelial cell route, you could block endothelial cell production of endothelin, which we didn't really talk about much, but it activates a receptor like the alpha-1 receptor. You could, anything along the pathway, like we just said, that would cause the production of nitric oxide, would cause relaxation of the muscle. So again, it's like, I love this question because when you first look at it, I noticed Kaylee Quackenbush was like, oh my God, I have no idea. But when you think about it and you understand how it works, there are hundreds of answers to this question. You have to, and what I want to get across is the idea of pharmacology, which is you figure out the pathway and then you find a drug that's going to activate or inhibit somewhere in that pathway. That's what pharmacology is all about. Okay. I should have a dental degree. What?
How about epinephrine in alpha-1 and in beta receptors? What does it do? Does it relax it?
Alpha-1 receptors? Well,
yeah, epinephrine in alpha-1.
Yeah, epinephrine will also activate alpha-1 and cause contraction.
Contraction or relaxation?
Yeah. Whenever the alpha receptor gets activated, you get contraction. So if you're talking about, I just got confused because I look down here and I see the term a-hole. And I'm like, wait, did I write that? Oh, a hole. Okay, sorry. But when you talk about epinephrine versus norepinephrine, what matters is for the response is what receptors are there. So no matter whether it's epinephrine or norepinephrine, if there are only alpha receptors there, you get contraction. Now, the difference is when you get into like the vessels that lead to smooth muscle, because then you've got both beta and alpha. So norepinephrine is going to hit those alphas and contract, but epinephrine is going to hit the betas and relax.
All right. Okay.
That's where the difference is.
All right. Thank you.
Okay. Methamphetamine, one of my favorite drugs. Not because I've never used it, but I mean, it's an interesting mechanism. Methamphetamine produces effects by inhibiting the reuptake of norepinephrine. Sort of. This is I wrote this a long time ago. I think it actually causes release of norepinephrine. In the central nervous system, this produces a feeling of euphoria and a heightened state of arousal. However, acute amphetamine toxicity has been known to cause aneurysm, which is not actually a hole, but like a ballooning of the artery that causes instant death. The artery like has a weakened part and it balloons out, and once it bursts, the blood just comes out and you die. Considering the effects of norepinephrine on the vasculature in the heart, why would you expect to see this effect? Why do you think you get aneurysms when you overdo methamphetamine?
Is it because since you're inhibiting the reuptake of norepinephrine, the cell's being like continuously stimulated?
Mm-hmm.
So like it's going through like muscle fatigue eventually, and then, or no?
Not much the vessel itself, but what all is going on with norepinephrine in the heart and the vasculature?
Contraction?
Contraction of the vasculature, yes. What about the heart? Ariana, what does norepinephrine do in the heart?
Doesn't it increase the heart rate?
Yep, and increase what else?
Blood pressure.
Correct. It's going to increase blood pressure both because of an increase in heart rate and an increase in contractility, right? The muscle is going to contract stronger. So you get a larger amount of blood getting out. And we're going to get into the specifics of that next week. But okay, so you're increasing cardiac output, right? More blood going to the vasculature, and you're contracting the vasculature at the same time. What's going to happen to blood pressure? Matt. Okay, you're putting more blood into this balloon and you're squeezing the outside of the balloon. What happens to the pressure? Does it go up or down? Just say it goes up. Did you say anything? What'd you say? Did you say, just say up? It goes up. Okay, good, thank you. So the idea with this question is basically, when you've got all this norepinephrine in your system, your arteries are contracting and your heart's putting more blood into the arteries, so the pressure goes sky high. And that's why, if you've got a slight weakening in the wall of one of your arteries, it'll just balloon out and then explode and die, and you die. So that's what I'm trying to get at here. The idea that too much norepinephrine causes an increase in cardiac output. At the same time, it decreases or increases your peripheral resistance. Wow, this is hard. I mean, you guys, the background of this paper. The background of the paper. You're not going to get this one. All right, I'll just.
Professor?
Yes.
Before we move on to the fourth question, the third question, what does an increase in the venous return to the heart? How does it affect it?
Okay, we'll definitely talk about this next week, but that's another mechanism that the sympathetic nervous system uses to increase cardiac output, because you squeeze the venous and you get more venous return, and then during the filling part of the cardiac cycle, you get more blood in the ventricle, and then you got more blood to put out. But that's a really important mechanism too. Okay. Any other questions?
No, thanks.
Okay, so this one, what's different? The paper we read was different. It said something different than what we said in class. And I'm just going to tell you because I'm getting old. Cycle. Where is it? Where is it? I think this is it. Nope. I know I'm not sharing it with you. I have to dig it up first. Oh, here it is. All right. So I just wanted to point this out because it's something I told you a couple of weeks ago. This is lecture 5, and it turns out I was wrong about something. So pKa phosphorylation target. So in that paper, they were talking about hyperphosphorylation of the ryanodine receptor. And they were saying phosphorylation of the ryanodine receptor plus oxidation causes FKBP to come off. And what I said was that this gets phosphorylated. So this was not right. Calstebin, or calstebin, it's been described. You're seeing behind the scenes here. I don't often let people behind the scenes in my slide making. I hope you appreciate it. Okay, so we're going to change this. Another way that just review all of this. So when you activate beta 1 receptors in the ventricle, how do you get a stronger contraction? One thing is you phosphorylate the VDCCs, so you get more trigger calcium. You phosphorylate phospholamban, so that you get disinhibition of the circa. So phospholamban comes off the circa, you pump more calcium into the SR, so you've got more to release. So that increases the relaxation rate as well as increasing the ability to contract. And you phosphorylate the ryanodine receptor, and that ryanodine receptor then phosphorylation makes the FKBP come off, the calstabin or calstabin. And so once the FKB comes off, that disinhibits the ryanodine receptor, so you get more calcium coming out per trigger calcium. So all these things are going to give you a stronger contraction. And then also increasing the relaxation rate, this phospholamban thing also increases the relaxation rate, and the phosphorylation of troponin I is decreasing sensitivity of calcium, so that causes it to relax faster. And also PPI, protein phosphatase inhibitor, inhibits the phosphatase. So again, when I was saying at the beginning how you should be able to see the whole thing in your mind at this point, you know, again, if your blood pressure drops, I talked about the reflex arc coming over the SA node. You also have the same reflex arc coming over to the ventricle, causing a stronger contraction. So you should be able to say, okay, that post-ganglionic sympathetic neuron is going to release norepinephrine on the ventricle. It's going to activate beta 1 receptors, increases cyclic AMP. Cyclic AMP activates protein kinase A, and that phosphorylates these 5 targets. Okay, you should have that whole kind of thing in your head.
On that last slide, what did you say happens to FKBP?
So it basically comes off the ryanodine receptor. So when the ryanodine receptor is phosphorylated, FKBP comes off of it, and that allows it to, that lets it open longer so you get more calcium coming out. That was in the paper we read last Thursday, or that I read, I should say. Okay, what else we got? Okay, so I sent you a quiz today by email, via the email system. And I'm going to pull it up now. We're going to talk about it because I'm angry. Where's my temp folder? There it is. There it is. Share. Okay. Here's a quiz. This is an old one. I put it up today, but I've had it for a while because I think it's good. This is touching on some things we haven't really talked about too much, but I think it kind of follows on what we've already said. So I think it's fair. It's fair. Okay, nicotine is a drug that activates nicotinic receptors in the ganglia of both sympathetic and parasympathetic neurons. What would be the effect, increasing, decreasing, or both, basically, of nicotine on heart rate? Okay, so you're going to activate both parasympathetic and sympathetic. What do you think that's going to do to heart rate? Matt? Up. Matt says up. It's true. I mean, I would probably put a Q because I don't really know. They're both activated. It may not do much of anything, but in reality, it does increase heart rate. So that shows you that the sympathetic system is more in charge there. Okay, venous return. I think Noemi asked me a venous return question. What is if you, oh, this is good. So if you stimulate both sympathetic and parasympathetic, what happens to venous return, Noemi? Does it increase or decrease?
Increase?
Increase, right.
As well?
That's right. So the way you want to think about this is, what is the innervation of the venous system? It's only sympathetic. There's no parasympathetic innervation in any of the vasculature. So if you activate both sympathetic and parasympathetic, you're only going to get the sympathetic response. Okay, let's skip over cardiac output because that is more complicated. Total peripheral resistance. In other words, resistance in the arteries. Is that going to go up or down? Tyler Montano.
It's going to increase.
Going to increase, right? Why?
Because we have heart rate and venous return increasing.
Well, we're only talking about, let's just say directly. What's it directly going to do to total peripheral resistance, and why?
It's going to cause vasoconstriction, so resistance would have to increase.
Correct, because we only have sympathetic input here, and so it's going to increase. Okay, so we've increased heart rate, we've increased venous return, we've increased peripheral resistance. What's going to happen to blood pressure? Dante.
Would it increase?
Increase, definitely. Okay, you're putting more blood into the system and you're contracting the system at the same time. Blood pressure is going to go up. And we'll go over that next week for the next system, but that's more or less what we're talking about here. So what do you think nicotine's associated with heart disease? You've got chronically elevated blood pressure, and that's not good. We'll talk about that in the next section too. All right. Let's, oops, okay. All right, we still have half an hour left. Let me go through the PowerPoints that I've presented so far for this section and just hit the highlights of them, because it seems like everyone's pretty lost. I get the sense we're not studying very much yet. So let's go through this and see what we don't know. Okay, what did it start? I think it started on 7. Okay, so remember your structure of the smooth muscle, of the artery, I mean. This elastic lamina on both sides of it, we'll talk about more next week. Varicosities, right? So with the sympathetic nervous system here in the vasculature, you don't have like an axon coming down to a blunt end for an axon bulb. It's just these varicosities along the axon, and each of them releases norepinephrine. And let's see, here's our contraction. The agonist hits the G protein, activating phospholipase C, breaking down PIP into diacylglycerol and IP3. IP3 then activates the IP3 receptor. Calcium comes out, binds to calmodulin, binds to myosin light chain kinase. Myosin light chain kinase then phosphorylates the light chains. The myosin elongates and forms the contractile apparatus. On the other side, you've got protein kinase C, which can phosphorylate caldesmin and make it come off, or this calmodulin could also bring that caldesmin off. And now you've got actin and myosin together causing contraction. Okay, so that's your contraction of smooth muscle. With the no calcium way of contracting then involves the activation of, who said this? Mike said this. G protein, which activates Rho. Rho activates ROC. ROC phosphorylates these two proteins, and they inhibit myosin light chain phosphatase. And then you no longer can dephosphorylate the myosin light chains, and so you maintain a contraction without calcium. This is just a different way of looking at it. Here you can see how the actin microfilaments are connected to those dense bodies. Back. There. So here's the dense bodies. Deep. Important for contraction. And I think the reason I put this up there was only because here, this is what we just talked about, but then here you can see that the microfilaments, the actin, are connected to this dense body structure here, and that is why when you get cross-bridge cycling, the cell shortens. It pulls all of that together. Oh, and that's it for smooth muscle. Okay. Number 8. Moving on from 7 to 8. Where's 8? There's no 8. Why is there no 8? All right, okay, give me a second. 8 is here. Okay, the heart. The heart. Remember the anatomy of the heart? Make sure you know this. Just kidding. Okay, anatomy of the heart. Make sure you know your heart valves. Mitral valve being really important. That's between the atria and the ventricle in the left side. Over here. No, that's left. This is left. Okay, and the left side, your mitral valve is there, and then you've got your aortic semilunar valve here. Over on the pulmonary side, you've got your pulmonary semilunar valve, which is here. And then this, what is this called? Tricuspid valve, I think. Okay, so make sure you know your valves, because it's important when we talk about the cardiac cycle, which valves are open and which valves are closed. Conduction pathways in the heart, SA node, AV node, bundle of His, and Purkinje fibers, right? That's the conducting pathway in the heart. Make sure you know that. Here's our pressure volume loop. So here you've got dramatic diastolic filling. The volume's going way up here, but the pressure's not increasing much, okay? Pressure only increases a little bit while the volume increases dramatically. And that's because that ventricle will stretch an awful lot when it's in relaxation mode. And then here, the muscle starts to contract. So we go through a period of isovolumic contraction. So the pressure inside the ventricle is lower than the aorta. So it's pressing against it without changing volume until at this point, the aortic valve opens because the pressure in the ventricle is higher than that in the aorta. And then the blood comes out. And as it does, pressure goes up in the aorta. And then the ventricle starts to relax, pressure goes down in the ventricle, and you get to a point where the ventricle, the pressure in the aorta is higher than the ventricle, and that closes. So here's your diastolic blood pressure there, where the aortic valve opens, your systolic blood pressure here, where the aortic valve closes. And now you get this isovolumic relaxation. So you've got both the aortic valve closed and the mitral valve closed. So the muscle is relaxing, so the pressure is going down, but the volume staying constant. And then when you get the pressure lower in the ventricle than in the atria, the mitral valve opens and it starts filling again. That's your cardiac cycle. Make sure you know that. And this is really good too. So it's another way of looking at it. Let's not worry about the atria. This is ventricular pressure. So, okay, so your atria contracts and that forces blood into your ventricle, and ventricular pressure goes up. And then here's where your ventricle starts to contract, your isovolumic, until the semilunar valves open, and then pressure continues to increase in the heart until it starts to relax. And then it gets to a point where the semilunar valves close, and you're getting isovolumic relaxation as you come down here. And you always get this dicrotic notch in blood pressure. And that's because of the semilunar valves closing, and then the blood in the aorta kind of sloshes back and pressure increases, and then it flows out. And your heart sounds, make sure you know your heart sounds. First heart sound is when that aortic semilunar valve opens and it snaps open and the blood hits the walls of the aorta really hard and you get the lub. And then when that same valve closes again and blood rushes back and hits it, you get the second sound, the dub. Lub dub, lub dub, lub dub, lub dub. So if you're unfamiliar with the lub dub sound, you should listen to the album Dark Side of the Moon by Pink Floyd. It both starts and ends with that sound. Okay. Electrocardiogram, Dougie. So basically, we're measuring the changes in electrical changes in depolarization or repolarization across the heart. So we're not looking at any particular cell, but just whole heart stuff. Here's your EKG. P is the depolarization of the atria, and they'll contract shortly after they depolarize. And here's your PR segment, which is the time that the action potential is going through the AV node. So it's slowed down there so that atria can have a chance to contract before the ventricle starts to contract. So in this period, you've got it going through the AV node, hitting the bundle of His, going down to the bottom of the heart, and then up the Purkinje fibers to stimulate the whole heart, and then depolarization of the ventricles. Okay, so it's QRS then is depolarization of the ventricles. And then you've got this ST segment, which is like right before, kind of the period before the ventricles repolarize. And the T wave then is the repolarization. Okay. Oh, it's right here. Okay, and here you can watch it in a different way, and here you can watch it in a different way, but it's all the same thing. This is pretty cool. I think you should like sit and watch this for a while because you can see how it's all connected. Okay, let's close that. That's 8. Sharon is Karen. Karen is Sharon. Okay, cardiac action potentials. This is really important. I know the guy who wrote the test and he told me this is probably going to be on it. So big difference here between the cardiac action potentials are this guy, SA node, is very similar to this guy, AV node, right? They both have this spontaneous depolarization section. And also, you've got kind of a less steep upsweep here than the other ones. So these other ones have a really steep upsweep and then this plateau period. And these have got a less steep plateau period and less steep depolarization and no plateau at all. Okay, that's the big difference between these two. And that upsweep part, the slow depolarization, is our funny current, causing depolarization of the cell. And then this slow upsweep is because you don't have any Voltspinnet sodium channels here. This is only a Voltspinnet calcium channel phenomenon. So in the atria, Purkinje fibers, bundle of His, ventricle, all of these things, oops. Oh, shit. Hang on a second. Okay, so in all of these other tissues, you've got sodium channels give you a really steep rise, and in the SA and AV, you don't, so you've got a less steep rise. And the other thing is this prominent plateau phase, which is again Voltspinnet calcium channels, which they're kind of inactivating here so that you don't get a plateau. But here you've got both Voltspinnet calcium channels and potassium channels giving you that plateau. And remember that the plateau is the trigger calcium coming in, causing contraction. Make sure you know that, crapola. And here I explained it all. And there's a difference between sympathetic and parasympathetic. We talked about this today. Increasing cyclic AMP is going to increase the slope and increase the heart rate. PNS is going to decrease cyclic AMP and do the opposite. Okay, there's our ventricle, atrial. Here's our SA node. Remember, the SA node is slowly depolarizing, but the stimulation from above, from the SA node, hits it before it hits the AV node, and that's why the heart rate is being driven by the SA node. But if you lose your SA node, you still have this secondary pacemaker. And there's your ventricular action Who's that? I don't know how to shut this off, so we're just going to talk through it. Oh, okay. So that's chapter 9. And here we are, chapter 10, ANS. Okay, so this chapter is going to have a lot of memorization to it. Just accept that. You're going to have to memorize a lot of stuff in this chapter. So what does ANS do? Housekeeping functions. Here's the structure of it. Fight or flight, rest and digest. Okay, so here's that reflex pathway that I was talking about the first thing today, and how your baroreceptor picks up a change in blood pressure that goes back through the dorsal root to your brain, your medulla oblongata, comes back out through the efferent pathways to the SA node or whatever, and that changes the physiology. So make sure you know everything in that pathway. There it is. And then anatomy-wise, you've got your vagus, which is the 10th vagal nerve, the 10th cranial nerve, and then you've got the pelvic nerve coming down here. So your parasympathetic is above and below the sympathetic. Sympathetic, short preganglionic, long postganglionic, parasympathetic, a long preganglionic, short post. Both of these synapses are nicotinic. And then you've got your effector, which in the sympathetic is usually norepinephrine, and in the parasympathetic it's always acetylcholine. Here's a $15 question. What is the only synapse of the sympathetic nervous system at the effector junction that uses acetylcholine? James Faraci.
Sweat glands?
Sweat glands, excellent, excellent. And that's why if you block muscarinic receptors, your skin gets very hot and dry. Okay. Oh, and there we are. Oh, and here. So now the point, when I told you have to memorize stuff, this is what I want you to memorize. What are the receptors and what are the drugs that are going to affect them? So at the nicotinic junction, at the neuromuscular junction, I'm not that interested in this because that's not cardiovascular. But here at the ganglia, we've got this drug hexamethonium that's going to block both sympathetic and parasympathetic. We've really got no agonist for this except nicotine. At the muscarinic junctions, which are parasympathetic, and the sweat glands, you've got agonists like carbachol, and these are important antagonists. You'll see these everywhere. Atropine and scopolamine. Scopolamine is the one that you put a patch behind your ear if you get motion sickness, and helps with that, because the muscarinic receptors in your tummy, your GI tract, when they get overstimulated, you get sick and you get ready to throw up. So this kind of blocks that. Okay, subtypes of muscarinic receptor. Just know that there's a subtype that activates IP3, and there's another subtype that inhibits cyclic AMP. So just worry about saying you've got your M1s that activate IP3 calcium, causing contraction or whatever. And then the M2s are decreasing cyclic AMP, and that's mainly SA node and in the ventricle, giving you the opposite of the sympathetic. Okay, alpha adrenergic receptors. Now these are really, really important in adrenergic pharmacology, because this is where a lot of your blood pressure drugs are going to come in. So alpha-1 receptors, your agonists, phenylephrine, that nasal spray that contracts the tissues and opens your nasal passages. Alpha-1 antagonist, prazosin, which is used a lot clinically to decrease blood pressure. Alpha-2 receptors are those presynaptics, and they inhibit the release of norepinephrine by decreasing cyclic AMP. And our agonists there are clonidine and methyl-dopa. Those are used clinically to decrease blood pressure. Antagonist Yohimbe, which is, you can buy it in the store. I guess it's somewhat recreational, but I don't know. It kind of gives you a simulation. Non-selective antagonists, phentolamine and phenoxybenzamine. So phentolamine will block both alpha-1 and alpha-2, as will phenoxybenzamine, and POB here is irreversible. So when we're talking about spare receptors, this is a drug I was using to knock out alpha-1 receptors. beta receptors, these antagonists are really important too. Beta-1 antagonists, metoprolol, atenolol, those are used for blood pressure. Dobutamine will activate it. So if you're, say you're in a cardiogenic shock or something, you give dobutamine and you'll get the heart beating stronger by activating those beta-1 receptors. Beta-2 then are on the air passageways, and that's why your albuterol inhaler is used for that. And then an antagonist, butoxamine, again, something like a beta-2 antagonist is either if you want to cause someone to have asthma, an asthma attack, or just really experimentally. You would use this in the lab to work out what beta receptors are for. Non-specific antagonists, non-selective antagonists, propranolol, this has been used forever for blood pressure, protect the heart, stop your sympathetic nervous system from stimulating it. And isoproterenol, your non-selective agonist. And here, so once you know the receptors and the drugs that affect them, you also need to know where those receptors are and how it's going to affect what the drugs are going to do. So in the arteries, we have only alpha-1 receptors, right? So you're going to get contraction, except for the ones that go to skeletal muscle. And in the veins, we only get contraction, increasing venous return. The eye, mydriasis, which means it's going to make your eyes increase in size. GI tract, decreasing motility, hair follicles, erecti. So I always like to, the way I remember memorizing this in grad school is like alpha-1 is sympathetic nervous system. So if you're in a fight or flight situation, what do you want to happen? You want your blood pressure to go up, so you're contracting the arteries. You want to get more blood back to your heart so you can increase cardiac output. Your eyes open more so you can see better. Don't worry about your GI tract. We're not digesting food. We're going to be dead in 10 minutes if we don't get out of here. So don't worry about your GI tract. Decrease motility. You know, bring your hair up so you look big and strong, right? If you were a furred animal, you know, your hair would puff up. And then get more energy out there. Beta receptors, also sympathetic nervous system. What do you want? You want your heart rate up, and you want that conduction through the AV node faster, and you want the ventricle to contract stronger, more cardiac output, and you're also relaxing the arteries, the skeletal arteries that go to skeletal muscles. So you're getting more blood to your skeletal muscle. You're ready to fight or flee. And then we're going to dilate your coronary arteries, get more blood there to your heart, dilate your bronchial tube so you get more air in, and again, more energy. So the way you memorize this, where these receptors are and what they do, is by thinking about that fight or flight mechanism. You know, how do you get more blood to get more oxygen in your blood and more blood to your skeletal muscles so you can deal with the situation. And then we went through this, which I don't feel like going through again. And then this is the baroreceptor movie, which hopefully, or whatever, you should definitely see this if you hadn't yet. Oh my God, so much. Okay, guys, what is it? 10 minutes left. You have any questions about the exam? The format's going to be a little bit different. I'm only going to have 4 essay questions, which will be worth 40% of the test, and then a bunch of, you know, matching slash multiple choice, you know, and that will be worth 60% of the exam. I'm trying to I always try to spread the questions out over all of the material. So we'll see how that works. Preguntas?
Dr. Slish, may I talk to you after class?
Sure, absolutely. Okay, nothing else? Nobody else have any questions, comments? Ariana's like, just bring it on. Bring it on, I'm ready. No? Okay. I guess that was my, okay, go ahead.
It was actually about, can we still be submitting bonus points to you?
Oh, sure, yeah. If you got some videos or something, is that what you mean?
Yeah.
Okay, yeah, absolutely. And I'll put them up on Moodle. Okay. Any other questions, comments? You guys really need to study between now and Thursday. I'm sensing you don't know what you're talking about just yet, okay? Hopefully this review helped a bit, but get to work, all right? Bye, y'all. Everyone sign off. I'm going to talk to Dante for a minute.
Hey, so I'm sorry about the mishap with the final submission.
Okay.
I was just confused with the directions. So do you want each like subtopic to be organized with the YouTube link?
No, only the ones that you did. Whatever videos you did. Yeah, not the ones you found on YouTube.
And is that the final submission, or do you want like an MP4 submission?
No, just send me the YouTube links.
The YouTube links? Okay.
Because MP4s are big, and if everyone's giving me 5 MP4s, it gets really kind of crazy. Okay. So just send me the YouTube links. And
okay.
I told you to put it in the box and do that, but also send it to me by email because I don't have Moodle connection right now.
Okay. Okay. I'm really sorry about that, by the way.
That's okay. It happens. If you get that to me this morning, though, you're the last person to bring it in, and today I'm going to send everyone assignments on other people's videos to look at and criticize feedback.
Okay. I'm gonna do that right now. Okay.
Excellent. Excellent.
All right. And is this the exam open notebook or no?
Yeah,
okay.
It's open. Yeah.
Okay. All right. Thank you.
If you don't memorize it, at least know where to find it.
Okay. Perfect. All right. Thank you. See you in a little bit.
See you shortly. Yep.